Today we want to continue the study of the Kepler problem, which is a special case of objects that are under the influence of central forces. In the case of the Kepler problem, the potential energy of the object that is moving, it depends on a constant and the distance r, that is from the origin of the reference system to the object. Okay, the distance between the origin to the object. That is the form of the potential energy of the object. In this kind of motion, we can associate a Hamiltonian function, and for the Kepler problem, the Hamiltonian will be defined as p squared over 2m minus k over r. Okay, this will be the Hamiltonian associated to the Kepler problem. Another thing is that we are going to define the Poisson brackets. These are a very famous mathematical tool. We are going to define the Poisson brackets of two functions a and b, where, for example, in the context of classical mechanics, we are going to have that, for example, a will be a function of q dot, and maybe t, and b is going to be a function of q dot, and t. Okay? Or it can happen that maybe a will be a function of q, p, and t, or b a function of q, p, and t. For example, in this case, maybe we will have the Lagrangian, which is a function of q dot, and t, and for example, in this case, a or b could be, the Hamiltonian, because the Hamiltonian is a function of q, p, and t. So for example, for this kind of functions, we are going to define the Poisson brackets of a and b as, the partial derivative of a with respect to q times the partial derivative of b with respect to p minus the partial derivative of a with respect to p times the partial derivative of b with respect to q. Okay, this is just a definition for now. But another thing that we are maybe interested in is to calculate, for example, the derivative with respect to time of a function of these variables, maybe this or this again. So for example, what happens if we want to calculate the total derivative with respect to time of a, looking that a is a function of q, p, and t, and it's also important to notice that q is a function of time and p is a function of time. Okay? So if we want to calculate the derivative with respect to time of a, we are going to use the chain rule, because q is also a function of time and p. So in this case, if we want to calculate this, we are going to have the partial of a with respect to q times the derivative of q with respect to time plus the partial of a with respect to p times the derivative of p with respect to time, and then plus the partial of a with respect to time. Okay, this is just using general formulas from differential calculus. And we also know that, the Hamilton equations, that are also very famous in classical mechanics, say that q dot is equal to the partial derivative of the Hamiltonian with respect to p, and p dot is negative the partial of h with respect to q. Okay? In this case, we are assuming that the functions a are just of q, p, and t, but they can, in a general form, they can be defined as a of q1, q2, all the way up to qn, and then p1, p2, all the way up to pn, and then t. Okay, we are going to have actually n q's, n p's. Okay, so in that general case, we will have a sum from 1 to n for Q and for P. But in this case, we are just taking one variable Q and one variable P. Okay, so notice that here we have actually Q dot, and here we have P dot. Okay, because remember that Q dot is equal to the total derivative of Q with respect to time, and P dot is equal to the total derivative of P with respect to time. So we can rewrite that the total derivative of A with respect to time is equal to dA dQ Q dot plus dA dP P dot plus dA dt. Okay, but using the Hamilton equations, we see here that Q dot is equal to the partial of H with respect to P, and that is, we are going to get the partial of A with respect to Q times the partial of H with respect to P, and then here we are going to have P dot, but P dot is negative partial of H with respect to Q, and that multiplies this quantity over here, so we will have a negative here, the partial of A with respect to P times the partial of H with respect to Q, plus dA dt. Okay, and look that what we have here is actually the same as the definition of the Poisson brackets that we gave here. Okay, so we can say easily that the total derivative with respect to time of A is equal to the Poisson brackets between A and H plus the partial derivative of A with respect to time. And in the case where A does not depend explicitly on time, this partial derivative will be 0. Okay, that is where when A is equal to a function of just Q and P, the partial of A with respect to time will be 0, and that means that the total derivative with respect to time of A is going to be just the Poisson brackets between A and H. Okay, perfect. So it is the moment to introduce a quantity that we will see that will be conserved in the Kepler problem context. That quantity is the Laplace-Runge-Lenz Vector, and we are going to name it as A, which is going to be defined as P, the vectorial product between P and L, and then minus mk times the vector x divided by r. Okay, so with this formula here, we know that to calculate the derivative with respect to time of this quantity, we need to calculate the Poisson brackets between A and the Hamiltonian, which we said that is defined with this. Okay, so an important thing to notice here is that we here calculate the Poisson brackets for two functions that are scalar functions. So looking at the Laplace-Runge-Lenz is a vector, we need to take a general component of that vector to calculate the Poisson brackets with H. So that means that we are going to take a component, for example, AI, which will be the component AI of this vectorial product, minus mk, with the component xi over r. Okay, we are taking the component I of the vector. Okay, and we are going to do it with the index notations to make it easier. That means that, for example, if P can be represented as Pi, Ei, where Ei is the unit vector in the direction of Ei, that means that the dot product P dot P, which is P squared, is going to be just Pi. Okay, and we have a very famous formula to calculate vectorial products. For example, if we want to calculate the I component of this vectorial product, that is going to be the Levi-Civita symbol I M N P M L N. Okay, this is a a formula that we are not going to show in this video, but we are going to use it because it will be very useful. So if we want to calculate the Poisson brackets A with H, A sub I with H, well, this is going to be the Poisson brackets between AIMN PMLN minus MKXI over R with H. Okay, perfect. So here we are going to use the properties of the Poisson brackets. In this case, looking that the Levi-Civita symbol is a constant, we are going to take it out from the brackets, and also this quantity over here, we are going to take it out. So that is going to give us the next EIMN, and we are going to split the Poisson brackets, this with H and this with H, to get two Poisson brackets. That will be PMLN, H minus MK, the Poisson brackets XI over R, H. Okay, perfect. Again, using the properties of the Poisson brackets, here we are going to get PM, the Poisson brackets of Ln with H, plus the Poisson brackets of PM with H times Ln. Okay, and then, well, we are going to remain the same here, Xi over R with H. Here, we know, well, we just said that the way to calculate the derivative with respect to time of a quantity is to take the Poisson brackets of that quantity with H. So that means that what we have here is equal to the derivative with respect to time of the angular momentum. Okay, but we know that in the context of the Kepler problem, there are no external forces that changes the angular momentum. So that is a quantity that is conserved in the Kepler problem. That means that this derivative is zero, making that all this quantity is zero. Okay, so we are going to cancel it. So we are going to get that this is EIMN times the Poisson brackets of PM with H times Ln minus MK times the Poisson brackets of Xi over R, H. Okay. Okay, so now we want to calculate these two quantities that we have here. I think that will be maybe the most difficult part of the video, but not that much. What we are going to do is to remember that we defined PM dot as, well, the Poisson brackets between P, H, and, well, we also said that this is actually a Hamilton equation where we can define this as minus the derivative of H with respect to xm. And I'm using x because in the context of the Kepler problem, the generalized coordinates q, p are, well, x, p, okay? The position and the momentum. So we are going to use this to calculate this Poisson bracket over here. And we know that, well, the Hamiltonian, well, we are going to have here that this is minus the partial derivative with respect to xm of the Hamiltonian, but the Hamiltonian is pi over 2m minus k over r. Okay, that is what we saw that it is the Hamiltonian defined as. So here we need to notice that, well, the partial derivative with respect to xm of pi is going to be 0, okay, because pi does not depend on x. Okay, so in this case, this partial derivative will only be applied to this term over here. So this is going to be equal to k times the partial derivative with respect to xm of 1 over r, taking out the k because it is a constant. And looking that r is the magnitude of the vector x, we have this. Okay, well, we can express this as, well, xl times xl raised to the 1/2 power. Okay, is just the magnitude of the vector. Look that here we have the dot product. Okay, x1 x squared plus x2 squared plus x3 x squared raised to the 1/2 power. So the magnitude of r is equal to this, but in the index notation that will be more useful in this case. So here we are going to have that this is k times the partial derivative with respect to xm of 1 over r, but 1 over r will be this quantity raised to the negative 1/2. Okay, so if we take the derivative of this, we are going to get minus k over 2 times xl minus 3 over 2 times, well, the derivative of this with respect to xm. Okay, but that is like if we had xl squared, so we are going to take 2 down here, then times xl, and then you are going to see that this is 2xl, and then the partial derivative of xl with respect to xm. Here we have a very interesting quantity. In this case, well, for example, let's say that L is equal to m. When L is equal to m, we are just going to get 1 because the derivative of xm with respect to xm is equal to 1. But all the other cases where L is different to m will be 0. Okay? So that means that we are going to have a Kronecker delta Lm. Okay? It will be 1 just when L is equal to m, and will be 0 if L is different to m. Okay? So if we cancel these 2's, we are going to get that this is minus k times xl Kronecker delta Lm over, and we are going to write this as xl raised to the negative 1/2 and then raised to the 3rd power. Okay, so this is equal to minus k, and here remember that we mentioned that this is just going to be 0 if L is different to m, but it will be equal to 1 when L is equal to m. So just is going to survive xm. Okay, so this is equal to xm over, and this quantity that we have here, which is actually, this is positive, this quantity over here is r, and we are going to have r to the 3rd power. So this is equal to the Poisson brackets between Pm and h. And a formula that we want to save because we are going to use it later on is that the partial derivative with respect to xm of 1 over r is equal to minus xm over r cubed. Okay, we are going to use it later. Okay, so now we want to calculate this Poisson bracket over here, the one that is xi over r with h, and we're going to do it with the definition. So this is going to be the partial derivative with respect to xm of xi over r times the partial derivative with respect to Pm of h minus the partial derivative with respect to Pm of xi over r times the partial derivative with respect to xm of h. Okay, first of all, it is easy to notice that this quantity is going to be 0 because this does not depend on Pm. So this is just going to be, well, here we have a product of 2 functions, so we are going to use the product rule, and this is going to be 1 over r times the partial with respect to xm of xi plus xi, the partial with respect to xm of 1 over r. And this all multiplies all the partial derivative with respect to Pm of h, but h, remember the definition that we gave, it is PL over 2m. I just switched the indexes for, well, I switched L for I, and then minus k over r. Again, it is easy to notice that this quantity does not depend on Pm, so when we take the partial derivative with respect to Pm, this is going to be 0. Perfect. So we are going to have 1 over r here. Here we have a Kronecker delta again. This is the Kronecker delta Im. Kronecker delta Im here, then plus xi, and then, well, we have the derivative that we just calculated over here. So that means that we can substitute this result to get that here we have a minus, and this multiplies xm all over r cubed. And this multiplies, well, the derivative with respect to pm of PL over 2m. Okay, but we are going to calculate now that we are going to get that, well, that will be 2PL Kronecker delta Lm over 2m. Okay, because this is like PL squared. Okay, if we take the derivative, we take the 2 here times PL times the derivative of PL with respect to Pm, but that is the Kronecker delta Lm. We eliminate these 2's, okay, and then, well, we are going to get the next. This is 1 over r Kronecker delta Im minus xi xm over r cubed, and here, looking that we have a Kronecker delta Lm, well, just the term Pm is going to survive. So we have here Pm over m, and this is equal to Pm Kronecker delta Im over Rm minus xi over mr cubed times xm Pm. Okay, and looking at that again, we have a Kronecker delta here, just the Pi term is going to survive, and we are going to get Pi over mr minus xi over mr cubed, and here this term is very interesting because it's actually a dot product between x and p, okay, just in index notation. So this can be seen as x dot p. Okay, so that is the Poisson bracket of xi over r with h. Okay, so if we substitute the results that we just found, we are going to get that the Poisson brackets between ai and h is going to be EIMN times, well, this result over here, minus kxm over r cubed times ln, and then minus mk times pi over mr minus xi over mr cubed x dot p. Okay, perfect. So if we develop this, is going to be minus k EIMN xm ln over r cubed, then minus k pi over r plus k xi over r cubed x dot p. And look at what we have here. It's very interesting. This is the I component of the vectorial product between x and L. Okay, this is x product ln and the I component. Okay, why is the I component? Due to the index of the Levi-Civita symbol here. Okay, so this can be rewritten as minus k over r cubed times x times ln I minus k pi over r plus k xi over r cubed x dot p. Look at what we have here is just the sum of I components of different vectors. Okay, so what we are going to do now is to use a vector identity, a very famous identity. But first of all, we are going to rewrite this as x cross x cross p. Okay, because the angular momentum is defined as x cross p. So, and we are going to use the next identity. X cross p can be written as, well, x times x dot p minus x dot x times p. Okay, and well, we are going to take the I component, so that will be xi pi, meaning that we don't need this arrow here. So, and x dot x is just x squared, which is actually r squared, because it's the magnitude of the vector squared. Okay, so we are going to put this identity on our equation. So we are going to get that the Poisson brackets between a and h is going to be minus k over r cubed times, well, xi times x dot p minus x squared pi, and let me write this as r squared, pi minus k pi over r plus kxi over r cubed x dot p. Okay, yeah, we're about to finish now. It is very easy to notice that this term is actually the same as this term, but with different sign. In this case we have a minus, a plus, so they cancel. And in this case, minus, it is a plus here. R squared can be cancelled with r cubed to get 1 over r, which is what we have here, 1 over r. So this term will be cancelling this term, making that this is all 0. That is what we wanted to show, because remember that the Poisson brackets of ai with h is equal to the total derivative with respect to time of ai, making that this is equal to 0. And looking that we are taking a general component of the Laplace-Runge-Lenz vector, well, every component will be conserved, will be a constant of motion. Okay, perfect. Okay, so that will be the final result of the video.